প্রচন্ড হাওয়া দিচ্ছে।
Okay, so is the screen visible?
Yes, sir.
Yes, it's visible.
Yeah. Okay. So today we'll be revisiting K-means. You've studied K-means in your week, but you haven't studied how to use K-means when you don't know how many clusters there are. So K-means num clusters. How can you, I mean, use a heuristic for the number of clusters? You can never predict that. And then we'll see some pass-fail cases for K-means. That is, when can you apply, when should you apply K-means, when you shouldn't apply K-means. So let's import the libraries first. We need this for plots. We need this for arrays. Then we'll have from sklearn import cluster and datasets. This is for synthetic datasets. And then we have K-means. Right. So let us create a synthetic dataset where we can control the factors. So this is a this is an sklearn function, make blobs. A blob is essentially a spherical cluster which is well suited for k-means, right? Because it simply computes the distance from each of the centroids. So it works well on spherical data sets, hyperspherical data sets. So it takes back. Let us go for this thing. Yeah. So it takes how many samples do you want, how many features do you want, how many centers should we create, and how much varied should the data be. So if we supply this, let's say we set n samples to be, let's say 500, and let's have a seed 30. So we use n samples as n samples. We'll ask it to create just 2 clusters, and let us say our variance is 1, and we set a random state. So doing this gives us two things. So the first is a set of coordinates, so x y x y x y, and then we have this thing. So these are the cluster assignments. So this is a synthetic data set. Now we can, by default, it creates a 2D data set. Here we can increase the number of dimensions. So for example, number of features by default 2, which means a Cartesian plane. So this is the data that one can plot. Okay, so let us plot the data. For plots, what do we need? We need x, y, and labels. So let's just say plt dot scatter, and we need x values and y values. So we can get that from blobs. So we have blob 0, and within blob 0 we have to take all of the first column, so all rows 0th column, and similarly um, all rows first column. So we have x, we have y, and we have labels like this. So we just give x, y, and we can say that the color is labels. So if we just plot this much, mm, x0 tuple indices must be integers or slices, not these. Oh, yeah. So we get these two clusters. So to improve the visualization a little bit, so let us say that we have X, Y, we have the color. I want my marker to be circular. I want the it to have edge colors. Let us say black, and I want them to be transparent to some extent so that I can check overlaps. So if we plot it now, slightly better. So we can see things like this. So here we can clearly see that there are only two clusters, and if I run k-means on this, I can specify clusters equal to 2. So before we move on to higher dimensions, let's first see how we can apply that. So we go to k-means and we say k-means is equal to k-means. Now what does k-means take? So sklearn k-means. So the first thing is obvious, the number of clusters. In this case, it is 2. The second thing is not this one. Yeah, here. Initialization. So this is important. K-means is a non-deterministic algorithm. A non-deterministic algorithm means the starting point changes the end result. In the beginning, because we have specified two clusters, it will pick any two random centroids to start with. It may so happen that, I mean, there are few cases where it may end up oscillating. There are few cases in which we get suboptimal results. So the idea is you can either pick random numbers or you can allow it to sample multiple times, which is k-means plus plus. It says it selects an initial cluster using sampling based on empirical probability distribution. Another thing is once you specify k-means plus plus or random, rather than running k-means once, you should run it multiple times. Okay. So one is how do you initialize? Then how many times should I initialize? So let us say I set the init to k-means plus plus. Then I ask it to do it, let us say thrice. So first time it would begin with some random initialization and it would compute the centroids. Now notice that we can calculate in a way the centroid quality. Okay, so for example, if I have two centroids, I can compute the distance to every point within the cluster, and I can basically take the average Euclidean distance. And if I have a smaller average, then it is a better cluster. Does that make sense?
Can you go over once more, like a little slowly? It was very fast.
Which part?
Like, just give a brief overview. Uh, like, I got that we created this PLT, and after that, when we are creating means, can you, slowly tell the n clusters and init and n init
Okay, okay,
descriptions,
okay.
basically.
So let's go over this part again. Yeah. So I said in k-means, it is obvious that you need to supply the k value. How many clusters are there? So this is obvious. The next thing is k-means is a non-deterministic algorithm. A deterministic algorithm means if you run it multiple times, you will always get the same results, right? But for k-means, if it in the beginning, it starts with random centroids. So it may so happen that I begin with this as a centroid and this as a centroid. And then I will do multiple iterations and I will settle down on something. When I run it the second time, it may pick this as the initial centroid and this as the initial centroid, and I let it run and it will stagnate. It may so happen that the two end results are not identical. That means a non-deterministic algorithm. The starting point changes the end point. Is that part clear?
Yes, it's clear.
Yeah. So then there are two options. So one is that you do it randomly, as is the normal case. Other one is k-means plus plus, as it has said. So K-means plus plus is just a sort of a heuristic. If we um, go here, so read this part. Selects initial clusters using sampling based on a probability distribution. Contribution to the overall inertia. Inertia here basically means the average distance from the centroid. So it essentially tries to pick a centroid that lies in the middle of the clusters. Okay, so for example, this is it sees this distribution. Rather than picking a cluster at the edge, it will try to pick a cluster somewhere in the middle so that the centroid is already in an optimal position, somewhat optimal position. Does that make sense?
Yeah, got it.
Yeah. So there are two options. One is k-means plus plus, obviously, and the other one is random. Now, if you use random or even when you use k-means plus plus, rather than running k-means once, you should run k-means multiple times. Now, why would you do that? Any guesses?
Because of the nature of this heuristic that it gets better with each iteration.
No, here number of iterations doesn't mean that I recompute the centroid that many times. Number of iterations mean I start from scratch this number of times.
Oh, okay.
Yeah, so
Then,
what you are saying is different. That is max iter. Let us say
okay.
max iter 30. I means run one iteration of k means 30 times. Num iteration means start from scratch 3 times.
Mhm. Okay.
So let me show you this part. So maximum number of iterations on a single run. N iteration says how many times should I restart? Now, why would I want to restart? The point is because of the non-deterministic nature, a restart may give me a better result than my current value. Now, can I basically judge whether my current result is better than the previous result? How would I do that? To do that, I use something called inertia. Inertia is just a fancy name of average distance from centroid. If my cluster is compact, that is, for example, in this case, I would prefer my one centroid to be here, another centroid to be here. That would give me a decent, the smallest average intra-cluster distance. That is within the purple cluster. This is the smallest that I can go with. If, for example, the centroid would have been at the edge, many other points would be far away. So the average distance would be larger, and that would result in a larger inertia. So when I do 3 iterations, it will begin with different random initial points. And every time it will see which random start gave me the best inertia. At the end, it will store the best one. Does that make sense?
Yeah, got it.
Yeah, essentially hit and trial. So we have said this part. So tolerance, verbose, and obviously random state. Then we have, let us say, random state. We set it to C and let us run it on this. So this, by the way, gives us an object we have to call fit on this. So we'll say clusters is equal to k-means dot fit. What do we give it? We give it the coordinates. So we give it the xy value. So we can just pass it, let us say, blobs, and it will compute the clusters. K-means plus plus. What did we give? K dash means plus plus. Setting an array with a sequence. Oh, yeah. So we have this part. So we can see clusters dot inertia. So this is the average distance over the clusters. We can also print the cluster centers. So these are the coordinates for the cluster centers. Now that we have plotted this part, let us maybe turn it into a function because we'll plot this again and again. So plot clusters takes in a let us say cluster, and we can optionally pass centers. What do we do with it? We simply take the coordinates, This is this part, cluster XY labels. Then we can say if centers is not none. If we are given the centers, we will also plot them. So we'll say plt dot scatter um, centers all rows 0, that is x value. Then we'll have the y values, all rows first column. Then I'll say this time mark it as an x. The size will set to 100. The color should be red and make it a little bit wider. So line width is 5, let's say. So I think this is okay. Yeah. So let us call the function here. We have plot clusters and we give it blobs. Plot clusters. Okay, so it works here. So let's maybe remove this part as well. So we don't want the ticks. So we'll say plt dot x ticks is blank. Plt dot y ticks is also blank. Okay, so now that we have this part, we have this part. Let us do it again. We'll say um, plot underscore clusters. This time we once again provided blobs. Um, should we provided blobs? Mhm. I think only this part, and we should remove labels, I guess. Hmm. Or maybe we can do this. We can pass it as an array. So we have blob 0 and we'll pass clusters dot labels. I think it comes like this. Yeah, clusters dot labels. So initially we had the original ground truth value. This time we want to supply the k-means assignments. So we have class blobs. Instead of blobs, we have this clusters dot labels, and we also have these centers. So that is equal to clusters dot cluster centers. Yeah. So we get these two centroids, works well. Now, what if we reuse this code? This time we had 2D data, which one can visualize. What if I have data that I cannot visualize? Okay, so let us say we keep everything the same, but rather than um, maybe 2 features, we'll set the number of features to 10. Now you cannot visualize a 10-dimensional data. So how can you decide how many clusters you have? Let us say we set the number of clusters to 4, and maybe because we have increased the dimension, we can also increase the number of points. So if we have this data, how do you identify that? There is something known as an elbow method. Elbow method is used in general to decide, to guess essentially how many clusters do you have. Now, what do you do in elbow method? You iterate over a guess. That is, you say, I think the number of clusters is between 2 and 10, let us say. So you will iterate over I in 2 and 10. You will apply k-means with k equal to I. Okay. So you will iterate over this. You will apply it with k equal to I. Once you apply k-means, compute the inertia. Okay. You compute the inertia. Then, by the way, can you fill the rest of it? Can you guess what we will do after this? Any idea? Should we pick the, k value with the least inertia? Okay, so what if I pick the k value with the least inertia? What will happen? In that case, it will always pick the largest number because the largest number means the largest number of clusters. More clusters means less points per cluster, and it also means smaller cluster. Smaller clusters means smaller average inertia. So we cannot just take the minimum inertia. Okay, does that make sense?
Somewhat.
So the idea is, for example, I start with two clusters up to 10 clusters. For every value of number of clusters, I compute the inertia. So can I or should I take that value of k that gives me the least inertia? If we do that, for example, even in this case, if I decide to make 10 clusters instead of just two, I'll end up with very small clusters. Does that make sense? And because
Yes, yes.
the clusters are small, every cluster will have small inertia because I points are very close to the centroid. And the average of those small values will also be small. So the highest number
Mhm.
will always have the least inertia. So we cannot do that. So instead, what we do is we record these values. That is, we record k against inertia, k versus inertia, and we plot this. So let's see what happens when we do that. So let us say, for example, we have set it to 4, we don't know it's 4. So we'll say, let us say for C in range 2 to 10, we'll start with 2, we'll end up with 10. I create a k-means object. Okay, so everything remains identical. We'll say number of clusters is equal to C. I want to initialize as k-means plus plus. I want you, because we're doing it multiple times, maybe do it just once for the sake of speed. I want you to iterate 300 times, and we can set random state as this. So this gives me k-means object. Then we can say clusters is equal to k-means dot fit, and we can pass it again blobs dot zero, which is essentially coordinates. So once we do that, what do? We want to store k against inertia. So let's say inertia is a dictionary. We say inertia C is equal to clusters dot inertia, right? So is anything missing? K means init got n cluster. N cluster, what do we supply? N cluster. Okay, so we have these values. Okay, so let us now plot these. So we have plt dot figure, plt dot plot, and we pass the keys and values. The x label is number of clusters, and the y label is inertia. Same dimensions, inertia keys, inertia values. Maybe a marker. So notice that this looks like an elbow, right? An arm. This is the bicep and this is the forearm. This point here at 4, this is known as the elbow point. And this is the best heuristic that you have for k-means. That's most probably the number of clusters is 5. This happens because up to this point you get significant gains when you increase the number of clusters. Beyond this point, the inertia doesn't change. Notice that it is still dipping, but it doesn't dip that significantly. So is this method clear? The elbow method?
Yes, got it.
Okay. So moving on. Let's go to some k-means fail cases. When does it work? When does it not work? So, yeah. So let us create once again blobs is equal to I think this is the easier case. Let's skip this part. So let us say we have, let me write this part. Okay. So this
Can
is
you show that code again for the elbow method?
Mhm.
Like I also did that, but I am getting kind of a different image. So maybe that's because of the random state.
Yeah, most probably because of the random state. And maybe your data is
Uh,
also different.
oh, the blobs were created randomly. That's why.
Yeah, I created the blobs again. This is 10D data and it also has a seed.
Okay. Okay, okay. Got it.
Yeah. So does it look like an elbow on your side?
Shall I show?
Yeah, you can do that.
Wait, wait, wait. Entire screen. Uh, I'm not getting the share button.
Just a minute.
Got it. So this is what I'm getting.
Yeah, you're not getting an elbow.
Hmm.
Maybe how many clusters did you set it to?
Like I copied most of what you did.
So the blobs is the old blobs.
The old blobs, yes,
Yeah, so I think the
like
point
this one.
is, I mean, for to see an elbow, there should be something before the elbow. So your the very first point is the elbow point. So you don't see the elbow. Do you see that? You're starting with 2 and you are increasing. So you're seeing a continuous dip. But because there is nothing
Okay.
before 2, you don't see the elbow.
So what should normally be like the starting point?
No, I mean, for example, since there are only 2 clusters, that's why the elbow
Mhm.
isn't visible. If you had
Okay.
maybe, let's say, 4 or 5 clusters, then you would see an elbow. So maybe change
Uh,
cluster number of centers, you should see an elbow, I think.
mm, Okay, I will try this maybe later. Yeah.
Okay.
Though I got the elbow actually with 5.
Yeah. So this part isn't important. I'm just creating a synthetic data set. Okay, so can you see this plot?
Yes.
Visible?
The screen has gotten smaller. Like previously
Now?
it was showing, yeah, better.
Yeah,
Little
so
bit more. Yeah, better.
yeah, so I'm saying, let's say we apply k-means to this. Clearly there are two clusters, right? So what do you hypothesize what will happen if we apply k-means to this? Where will the centroids be and what will the clusters look like?
The centers will probably at the U bend on both sides.
So here,
Yes.
so here for this one and here for this one.
Right.
So maybe here would be better, maybe here, because that makes it closer to all of these. And what would the cluster look like anyway? So let us say they are at the U bend. What would the clusters look like? Same?
No clue.
Hmm? Yeah,
I
Priya.
can't visualize. Yeah.
Yeah, Priya, go
Need
ahead.
more experience with this.
Yeah, I mean, just intuitively. Yeah, Priya, do you have a question? Your hand is raised. Okay, so let's apply k-means to this and see what happens. So we once again have, let's copy this part. K-means. So we have this part, k-means, the number of clusters. We know there are two clusters, 300 seed, everything remains the same. And then we say clusters is equal to k-means dot fit. This time we have crescents. We give it the coordinates and then we say plot underscore clusters, and our clusters are crescents, SCENTS, the coordinates and the predictions. So clusters dot labels, and then we have centers as clusters dot cluster underscore centers. So let's see how we do. CLUSTERS. Don't we have clusters? The cluster. So this remains the same. Module object is not subscriptable. But oh, mm, yeah. So returning to our problem, we had this. Yeah. So we get two clusters, but they don't look the way we expected them to. So can you now understand what happened? Why did k-means not pick the bend? How does k-means proceed? K-means starts with two random points. They are assigned as the centroids. For every point, we simply check which centroid is closer and we assign it to that. So for example, these points are very close to this centroid. and very far away from this one, even though they are clearly part of this cluster, but just because they are closer to this one, they are assigned to this cluster. Makes sense? So K-means has a flaw that it only works with spherical data. That is, when all directions are the same. In this case, more than direction, there is something else. There is a particular shape. There is sort of a connectivity within the cluster that K-means cannot pick. So this is one of the failure cases for K-means. Does it make sense? Do the cluster locations make sense?
Got it. Got.
Yeah. So let's try another one. This time, let us go for, yeah, let's go for these. So these were crescents. Okay, so we want rings. So again, ignore this part, okay? So what about this data set? We said K-means works with circular data. I'm giving it circular data. What do you think will happen? If I apply K-means to this, where will the centroids be? What will the clusters look like?
Maybe right in the center. The centroids will be
Both centroids, one of the centroids.
both of the centroids.
Both centroids?
Mhm.
So both.
Okay, so and what will the clusters look like? The same? Inner ring, outer ring? By the way,
Maybe.
these colors are not the K-means clusters. I mean this is the ground truth that we know these are two clusters. I'm asking what will it look after I apply K-means?
Mhm. Maybe same concentric rings.
Okay, so let us imagine it this way. So I have two clusters at the center, and a point is assigned to a cluster if it is closer to it, right? So why, if both of the clusters are in the center, why should the outer ring belong to one and not the other? They are sort of equidistant from either clusters, right?
Mhm. Right.
So if we try it out, we can just reuse this part. So everything remains the same. Instead of crescents, we have rings. Rings, two clusters, 300 iteration, everything is the same. Yeah. So does this make sense?
Yeah, I thought as much, but instead of this, like I thought it will be like vertically. But yeah.
I mean, yeah, just a rotation. So do you see why it does that? Because placing the centroids this way, it makes them equidistant from each other, and it takes half the ring. This one takes half the ring. Makes sense, everyone?
Right.
Ankur, Ritu. So K-means doesn't work with all circular or spherical structures. If they are coinciding or if one is sort of overlapping the other, it still fails because it doesn't have, again, that connectivity thing. It's just based on distance. So let's try a third case. This time we'll give it spherical structures that are distinguishable. So let us say we don't need this part. Wait. Let us say we create two centers, same number of points. One is has a little more variance than the other. Hmm, what do we set random state to? Let us say we have this, and what do we do then? We say plot clusters, this thing. Make gloves got, oh, okay. So what about this one? Both clusters are spherical. Can K-means pick these clusters, the purple one and the blue one, exactly like this as the ground truth?
It should.
Okay, so one of the centroids will be here in the middle of purple and the other one will be here, right?
Yeah, right, right.
Okay, so does anyone have different thoughts? Everyone agrees?
I agree.
Okay, so we have this, we come here, we have two clusters, 300 K means instead of rings. We once again have, no, we have varied density. So what's different is, I mean, I supplied the number of samples I believe to be 500, I think. 500, yes, 500. So there are 250 points purple, there are 250 points yellow. The only difference is they are very closely packed, tightly packed. These are sparse. So high density, low density. So let's pass this varied density. Everything else is same. Notice that the purple one ate up a lot of the yellow ones. You see that? This part here, these yellow ones were taken up by the purple cluster, even though they are clearly part of this one. So we see a repeated flaw in K-means. K-means disregards density. Think about this. What if this purple cluster was on top of the yellow cluster? As a human, we can still say that the dense part is one cluster, the sparse part is another cluster, but K-means will miserably fail on that, right? It will probably give right half to one cluster, left half to another cluster. Does that make sense?
Yes, yes.
Yes. So whenever there is, for example, this case, varied density, K-means doesn't care about density. All it cares about is distance. This is the dividing plane. Left of this, everything is this. Right of plane, everything is this. So let us do another one. Um, let's copy this one. So this was same size, varied density. Let us create same density, varied size. So we can reuse this part. So we have varied size, both have same density. So let's set them to 2 and 2. And this is varied size. And this time I'll ask it to have 10% of data in um, one of them and 90% of the data in another. Same density, different number of points per cluster. Mm, okay, so you don't need this. Okay, so what about this one? Same density, but more points here, less points here,
Same case as before, it will eat up into the other.
right? Same case as before. So let's plot this one. So even though the densities are identical, it still cannot do that. So this happens because k-means always tries to create clusters that are sort of equal in size. Okay. So if one of the clusters is small, even though the density is same, it will eat up the other cluster because it tries to create clusters that are sort of that have equal radius. It tries to balance the diameters. So k-means cluster varied density. Instead, we have varied size. And again, we have varied size. And if we plot this, so same, it ate up part of the yellow. So now let's, I think, move on to the last one. Mm, yeah, so let us say we have okay, what about this one? We've done this, right? This doesn't look spherical. So what about this? Three clusters. Let us say I supply three clusters. Where will the centroids be and what will it look like?
I think centroids will be like in the center of the box, uh, like closer to the edges where they are meeting, right?
So let's go one by one. So what about the yellow one? Where will its cluster in its centroid be?
Like a little bit upward side towards
Here,
the middle.
here.
Yeah, somewhere here, I think.
And what about these two?
Similarly, they will be a little below,
So here.
right?
But won't that make it quite far from these points? There are a lot of points on the left.
Hmm.
So I would
Like
expect one
yellow
of
one.
the yeah, so I would expect one of the centroids to be here because this one is far apart. So there might be competition between these two.
But there are more on the for the yellow one.
Mm-hmm.
It will be a little bit upward side only, I think.
Mm. Okay, so you're saying it may eat up some of these, right?
Hmm.
Yeah, so let's try that.
And purple one will definitely eat up the
Yeah,
this one.
correct, correct,
Blue.
correct. Exactly, exactly. So this time we have three clusters. This time, what do we call it? X cluster underscore trans. Expected, right? These two were quite
Yellow
together
moved
because there are,
completely.
yeah. No, I mean, this is not actually don't, I mean, attach the coloring. The coloring is random. So this yellow did not shift to this yellow actually. So these colors are just random. Notice the clusters that this ended up as one cluster. This is one cluster. This is one cluster. The colors
Mhm.
need not match.
Right.
So the point is these two competed with each other and took away from each other. This one ended up on its own.
Mhm.
So the point is, um, these three are not overlapping clusters. We know that by design, we know that there are equal number of points in all three of them. The only problem is they are not spherical, correct? So what if I I mean, we could transform, think about it. These are sort of lines, right? I can transform them to a space where I can sort of increase the gaps in one direction and decrease the gaps in other direction. I mean, it looks as if, to me, it looks like K-means should be able to do this because all of the clusters are away from each other. They are in straight lines. I mean, there is no overlap. For example, in this crescent case, uh, where is that? Crescent here. The problem is there is a circle. So even if I mean, I have to flatten this out for this to work out. But here they are already flattened out. The only thing is, I mean, that I have more variance in one direction than in another direction. And K-means fails because of that. If I could increase the variance in one direction and decrease it in the other direction, or in better said, have similar variance in all directions, K-means should be able to do this. So if you notice, essentially, when I made the data set, I initially started out with blobs. I actually transformed it using this matrix. I skewed the matrix. I shifted the Cartesian plane. So if I actually take the inverse of this transformation, I would get the original circular blobs back. And I can then create the cluster. So let me show you that. So we know the transformation in this case. So this is the transformation. If I do np dot linear algebra dot inverse, this will give me the inverse transformation. If I apply this to all of the points, I will once again get the original clusters back. So it would look something like this. So np dot linear algebra inverse will say np dot x underscore trans this, and we can say inv is equal to this guy and y remains the same, and we can say plot clusters inv, right? So again, the colors have changed, but notice that these three straight lines have converted to this. Now, the problem is in real life, I don't know the transformation, correct? So how will you transform this type of data to this type of data, circular data, where you can apply k-means? So I would implore you to read about whitening data. The way we standardize data. So what do you do in standardizing? You subtract the mean and you divide by the standard deviation. So essentially what that does is it brings everything in the range of 0 to 1. In whitening, you remove variance along directions. Okay. So when you do that, you get from this part to this part. This is known as whitening. This is also a pre-processing step that some of the machine learning methods use, whitening. So you can search data whitening. A whitening transformation is a linear transformation that transforms a vector with known covariance and so on, so on. So how can we do that in our code? So you can look this up after the lecture. So let us write a function for whiten data. So it takes x and it takes some tolerance. I'll tell you later about this. So let us keep it as, let us say, a very small number, epsilon. So the first is we have to get the covariance matrix. The covariance matrix computes the variance along x, along y, along xy, and so on. So we have the covariance matrix. Then you have to do eigenvalue decomposition. This tells you the direction of the major variance. And eigenvalues essentially tell you which are the transformation that when you apply the transformation, maximum amount of stretching or skewing is on along that line. So you have the eigenvalue decomposition. Then you compute the diagonal matrix. How do I write that? Diagonalize. Once you do that, you essentially compute white weights, compute whitening matrix. So I'm just glossing over it. You should read about it in depth after the lecture. So you compute the whitening matrix and then you just multiply with the data. The effect is that you basically compute these directions of maximum variance. You scale them down and you essentially remove the variance along all directions, ending up with spherical data. So obviously there is loss of information, but it is good for, clustering in our case. So how do we do that? So for covariance, we'll say, let us say x covariance is equal to np dot this x dot transpose with x itself. So we have the covariance matrix. Then we need the eigenvalues and the eigenvectors. We'll say np dot linear algebra dot EIGH, give it the covariance matrix. Then you diagonalize d is equal to np dot diag 1 by np dot sqrt d plus, and this is just a tolerance so that you don't divide by very small values. So you this, and then you have the diagonal matrix, then you compute this, and you return x white. So there is a simple form of this. I'll show you just in a minute. So this is the long form. So let us say we have this, and we say whiten data, and we pass x underscore trans 0. And this returns these two things. We only need the first one, or we can maybe write it like this. So white is equal to x white comma y, plot clusters white white data, whiten data. Zero dimensional array must be two dimensional where x underscore. Okay, so you see, we went from these three straight lines, we went to this. These are not identical to the actual inverse because there is obviously loss of information. So doing all of this is actually equal to a simpler function. If some of you are aware of SVD, support vector decomposition. So what you do in this case is, in support vector decomposition, again, you break down your entire space into directions of maximum variance. Maximum variance means most of the information is stored along those lines. So an SVD returns three things. You have U matrix, a V matrix, and in between you have a sigma matrix. Sigma is the scaling, and these two are orthogonal matrices. Essentially, what you want to do is you want to remove sigma part, that is different scaling along different directions. Notice that in U, all of the vectors essentially mean different directions. Every direction is scaled by some value by sigma. When you divide by sigma, you remove the scaling. So now every direction is scaled similarly. So you end up with circular clusters. So don't sweat about it if you don't know about SVD, but if you are interested, maybe read about whitening and maybe read about SVD in general after this. So let us say we have SVD whiten. We once again give it X. And what do? We need U, we get sigma, and we get V transpose. We say np dot linear algebra dot svd, and we give it X, and we say full matrices is false. That is, these may be rectangular matrices. Then we say X underscore Y is equal to np dot dot, and we just use U and VT. We remove sigma. So we say U comma VT, we are simply dropping this part. The multiplying these three, U, sigma, and VT, gives us X. Multiplying only the first and the last one essentially means I am removing sigma. So I have X white, and I can just return this part. So doing all of this is the same as doing all of these steps. So maybe this is easier to understand if you know what SVD is. So let us try this. We have X SVD is equal to SVD whiten. We once again give it X trans, and then we can say SVD is equal to X underscore SVD comma Y. Plot clusters SVD. Same. Any confusion?
Got it.
Yeah. So I think that's it for today. And I think, I mean, it's quite intuitive that if you apply K-means to this, it will work, right? These are almost spherical clusters. So we went from these two eating up each other from three separate clusters. Obviously, there is loss of information, but it works. I mean, in cases, I mean, if you had multi-dimensional data, it may not work, but anyway, you can try out whitening and then see, do I get better clusters or not? So what did we cover today? We started out with 2D data, which is quite easy to separate. Then we went to multi-dimensional data where you cannot visualize. There we saw that using the elbow method, you can start out with a heuristic. That is, probably the number of clusters is equal to the elbow or plus minus one or two clusters. Then we saw some failure cases for K-means. The first one is, for example, this type of data, Crescents. That is, you have some connectivity. Clearly, there are two clusters, but K-means cannot distinguish this connectivity because it goes by distance. Then we saw that even if you give it spherical data, but they're overlapping each other, that is, the radii are one is smaller than the other, K-means cannot work with that. It will just split the two rings in half. Instead of rings, if we in fact had superimposing clusters, it would still do the same thing. Half of it go to one thing, half of it goes to the other. Then we saw that, okay, let's give it two clusters. They are not overlapping, but one is more dense than the other. What happens then? Can you identify density? As a human, I can clearly say that these are one, these are the other one. We see that it doesn't happen. The differentiating plane is right in the middle of the two, and half goes here, half goes here. So what if I supply two data sets with two clusters with similar density but different number of points? Again, same thing happens. And finally, we saw that what if I have data that isn't spherical, but intuitively I can see that I can make it spherical. So what I do is whiten data to apply K-means. So when you see things like this, you can use whitening as a pre-processing step and then apply K-means. Any questions?
No, it's okay. Lot to
Okay,
absorb
so
today.
yeah. So see you all next week then.
Thank you for the session.
Yeah, you're welcome.